Michael Jordan. Yep. Oh, hey, geometry. All right, let's go. We're going to talk about proving segments, or, well, just proving line segments and proving distances, okay? The first thing they do in this section, it's a little embarrassing. This is such an easy postulate. It's called the ruler postulate. By the way, we have a studio audience today. You might want to take a shot of them. These lovely people.
Yeah! What's up, gamers?
What's up, gamers?
So, studio audience, does this make sense to you? If I have a line, I can put numbers on that line that stand for different things.
What?
Yeah, that's the ruler postulate, okay? It's kind of, I don't even honestly know why they have that in the book, but I'm just mentioning it. A postulate that you're going to use more of is called, it's a postulate 2.9. It's called the segment addition postulate. And my studio audience knows what postulates are, don't you?
Of course.
For sure.
Postulates are statements that don't really need any proof to know that they're true. They're just true. For instance, if I had a line segment and I had 3 points on it, A, B, and C. If B is between A and C, then the distance from A to B plus the distance from A to C, in other words, AB plus BC, that equals the distance from A to C. Got that?
Mm-hmm.
Do you see why you don't really need to prove it? It's kind of so obvious that it's like, yeah. Usually when you see a postulate, you kind of go, duh. They're self-explanatory almost. But then we're going to use these to prove other things. And that's what I really want this lesson to be about today, is we're going to do a more formal thing called a proof. And you guys don't know what that is, but next year you will love these. Proofs are a form of deductive reasoning where you're very rigid and you explain step by step by step. It's like a chain of things linked together that starts from one place and it eventually takes you to another place. You can't skip a link. You can't skip. They've got to be step by step by step going along, okay? So, think of an example. Oh, sorry. We're going to do what's called the two-column proof. I'll just write that up there. And then we're going to do a quick example and see if you guys can follow along, even though I know you guys haven't done this yet, okay? In your book, they give you a picture like this. And we're going to interrupt your regular scheduled content here. And I realized that in watching this over again that I made a little bit of a mistake, and I kind of just don't want to confuse you, okay? So here's my suggestion. If you're watching this video as your first introduction to proofs, I think you should actually stop, go back to my playlist on proofs, and I do a much more kind of step-by-step way to get into proofs, okay? You probably shouldn't watch this as your first introduction to proofs. If you've been introduced to proofs and you're just watching this for section 5 of chapter 2, then stay with me, okay? So let me just do a quick proof for you with using the segment addition postulate. Let's say that we have a line. We got W, X, Y, and Z. So, and they're going to give you, given the line segment WX is congruent to line segment YZ, prove that WY is congruent to XZ. So what I think you should do is, of course, you're doing a two-column proof. This side is going to be your statements. This side is going to be your reasons. Can you see that? Write down your given. Make sure you number things. And the reason for that is given. Now, I encourage you to stop at this point, look at where you're going, and try to come up with a strategy. Okay? So they're telling me that these two segments are the same. Well, I can see that if I have the same and I add it to something, and I have the same and I add it to that same thing, then those are going to be the same. So that's my strategy. Okay? Now, if I'm going to talk about adding segments, I can't be dealing with congruency. I have to be dealing with lengths. Okay? I need to be dealing with equals. So my first step is I'm simply going to transform this to an equation. So the distance from Wx equals the distance from y to z. And the reason for that is the definition of congruence. I'll just abbreviate it like that. Okay, so remember my strategy was I was going to show that, add it to the same thing. So step 3, the distance from W to x plus xy equals yz plus xy. So basically what I've done is I've just added the same thing to both sides of an equation. So what property is that? That is the addition property. When I combine these two things, I'm going to get the length that I want. So I need to show that Wx plus xy equals Wy. That's the property we just learned about, the segment addition postulate. Now, if I have something equal to a whole side of an equation, and then the same exact thing as a whole side of an equation equals something else, I can do what's called the transitive property. So I'm going to go from this Wy, cut out the middleman, and get all the way to this. That is the transitive property. You can just put trans if you want. Tell me what steps you're using. You're using steps 3 and 4. I'm going to do the same thing that I just did now for this side. Number 6, yz plus xy equals, that equals xz. That's the segment addition postulate. And now this thing equals that thing, so I can do transitive property one more time. And I'm almost home. Wy equals xz. Transitive property. And that is steps 5 and 6. You've almost proven what you want to prove, and now you just have to change equals back into congruency. A segment Wy is congruent to line segment xz. I hope this is readable. And the reason for that is just the definition of congruency. Okay. So that's how you would use the segment addition postulate. We'll practice much more, but that's a good little introduction, okay?